Okay, welcome back. This is a hashing implementation. So you need to write code, so don't wait till the last minute. Although it's not super hard once you understand what I'm asking you to do. But it is code, okay? We haven't done code in a little bit. So there's two parts. There's hashing with collision resolution, and then there's perfect hashing, okay? Two parts. So two separate programs, all right? Two separate programs. So I think what I'm going to do is go through this handout and then go through some of the data printouts and then maybe come back to this handout and see how that looks. All right, so in biology we often deal with very large data sets. All right, so hashing is a technique that's used. So that's why I'm talking about proteins in here, but they're really just strings. All right, so I want you to read strings from a file and count them. All right, and because there's going to be lots and lots of strings, we don't want to be searching all the time, right? So we want to do hashing, right, to avoid searching. Remember, hashing is big O of 1. It's constant time operation because you're going directly to where you need to go. So with regular hashing, you have to resolve the collisions. So I want you to make a user-created hash table. And what do I mean by that? I mean these structures that I've given you here. I don't want you to use some template file where it does all the work for you. I want you to use these structures here. So what I've got is a little structure that has a string in it, and then it has a count, right? By string, I mean a character array. It's just a simple character array, and then an integer for the count. So that's these two fields here. You've got the proteins, which are just strings, and then I've got how many, the count. So eventually, these are the two answers for these two particular strings. Eventually, that's what will be in these count fields. But you'll start off with 0, and you'll count up to these thousands. And you can use these numbers to check that you're getting the right answers. So there's information that we know, and let's read that. So you know that the file is very large, but somehow you know that the length of each string is no more than 30 characters long. I'm calling characters amino acids. So that's where this 30 comes from. You know that each string is no longer than 30. So this is enough room, 30, to fit. And you also know that there's no more than 20 unique values. So if we use a 40 element array, right, 0 through 39, then half of these spaces should be blank. And remember, for resolving collisions, we need to have at least one blank spot. Otherwise, you would never know when to stop looking. But if you have more room in here, more extra room, that reduces the chance that you're going to get a collision. So 40 elements, when we know there's only 20 unique values, that's half the data array is going to be empty. So that'll reduce the probability of collisions. And then with less collisions, there'll be less collision resolution, right? Less stepping around looking for what we want. So I want you to use this hash function. So the hash of the key is take the first letter of the key and add 2 times the second letter of the key and then mod the whole thing by 40. So for example, if you do this string here, B and blah, 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 and W. So basically, we're taking B plus 2 times W. And B, if you write the alphabet out, this is 0, 1, 2, 3, and this is 25, 24, 23, 22. So B plus W is 1 plus 2 times 22. It's 1 plus 44. It's 45. Oh, B is 1. It's 45, and 45 modulo 40 is 5. And you see I have a 3 here, which is wrong. So this should be 5. And the second value here, A plus 2 times D, is going to be 0 plus 2 times D is 3. So 0 plus 6 is 6, and 6 modulo 40 is 6. So this string, which I'm calling a protein. This protein here hashes to 6, and this one here hashes to 5. So what you're going to do is you're going to read in all of these strings here, proteins, and hash these indexes, and then update the counts. Okay, so bike, blah blah blah, will hash to 5, and AWG will hash to 6, but others might hash to 5 and 6 as well, right? There's other strings that might have the same indexes, so you need to resolve that. So I have a collision resolution algorithm. There's 3 cases, right? It's going to be when you hash a index and you go to this location, there's 3 cases, right? There's either the first case, could be blank, right? There could be nobody there. The second case is what you seek is already there. So it's how do I say that? It's the key is there. The third case is some other key is there. Right? So if it's blank, you write so this is, if, then. If it's blank, you write it there. And if some other key is there, you need to step. No. If the key that you're searching for is there, then you increment the count. Right? And if some other key is there, then you got to step the index. So that's what's coded up in this little algorithm right here, right? You read a protein in until you get to the end of the file. That's the outer loop. You hash the initial index, 5, 6, or something else. Then it's going to be one of these cases. If it's an empty spot, if it's blank, then you copy the key to the table and increment the count, and then break out of this inner loop. If it's somebody else is there, that's case 3. Wait, I messed that up. So, I messed it up. I did case 2 first. So, you hash the index. If you find a blank spot, you copy the key into the table, and then you increment the count and then break out. If you find the value that you're processing, then you found basically a duplicate value. So all you got to do is increment the count. That is, if the key is there, you increment the count. And otherwise, that's this some other key is there. Then you step. You increment the index, and you go back around and do the next. And then after you've incremented the index, you go back around and check these 3 same conditions again. So what I'm saying is, if you read some other string and it also hashes to 5, you're going to go here to this location, and this other key is already there. That's a collision. That's this third case in the code here. I think these are out of order with this. But anyway, then you'll step. You'll step to location 6, and somebody else is there. Or maybe that's who you seek, right? And in which case you would increment. Otherwise, you would keep stepping until you either find who you're looking for, or you find a blank spot, right? So that's this algorithm here. It's almost code. Okay, so that's that. The data that I've posted for you is this gigantic file. Now this is like megabytes. So you need to, in your browser, you need to save this as a TXT file, right? And then the other thing I've given you to help you out is this piece of code right here. This guy will open whatever file you want, and it just prints them out to the screen. But what you're going to do is, where I'm printing out to the screen, you're going to insert this algorithm right here, right? So you're going to take this algorithm here and stick it in stick it in here. So one more time, walk through what the processing might be here. So you're going to read this file, and you're going to have a big old array. So you read this guy. You'll hash some index. He might go here. Let's say he goes to location 42. I don't know what he is. And then you're going to read SCC, and it hashes to some other location. You write it there. Oh, and you increment the counts while you're doing this. Then you'll get down here. Well, let's do Dan. So let's say Dan happens to hash to 42. So you'd go here and somebody's there. So you're going to walk down to this location and write Dan, right? And then later on, you'll get to AEC. You'll hash 42. You'll go here. You'll increment this. And then maybe you'll get another Dan, right? So you'll hash 42 and you have to check this. That's not Dan, right? Same index, but it's a collision. So you step and you find Dan, the second Dan. Oh, this one was 1 already. So you find the second Dan, then you increment. Okay, that's kind of this algorithm right here, and stepping through it. All right, study that. It's not super hard when you figure out what it is I'm asking you to do. All right, that's part 1. Part 2, perfect hashing. Okay, so in order to do perfect hashing, you need to know the keys ahead of time. So I've given you those keys here hard-coded. So you could just copy and paste and throw that in your code. Now remember, with perfect hashing, there are no collisions. So there's no stepping, there's no checking. You don't even need to store the key, right? With regular hashing, you have to store the key value because you have to check if, because these two keys here could hash to the same initial index. So the only way to tell if you have a collision is to check the data you're trying to insert with the data that's there already. It could be the same. It could be another string that just happens to have the same index. Okay, so you have to store the key. But for perfect hashing, we don't need to store the key, just the counts, because there won't be any collisions. Each one of these key values will have a unique index, 0, 1, 2, 3, unique index. So all you got to do is read these words from a file, hash their index, and increment the count. And every one of these guys will have a unique index. So you're going to read. Where's my data file? Too many pieces of paper here. It's a big old file. It's also big old bytes. So do this, save it as a TXT file. There's lots and lots of these guys. New, and then here's new again, and new again, new again. There's at least 4 or 5 news, a couple of ints, stuff like that. But you'll read new, you'll calculate the index, you'll go to that location and increment the count. And you'll read int, go to that location, increment the count. And each one of these will be unique, so there's no need to resolve collisions. Now, the hard part is making sure that these guys hash to unique indexes. All right? So most of the work you're going to do on this implementation is getting the hashing function so that it works properly and has no collisions. So you need to create your own hashing function. What I'm suggesting is you do something that looks kind of like this and looks kind of like this, but I want you to change this unique for your particular solution. So it helps to have a lookup table. So H is the hash function and G is the lookup table. H and G, they're both kinds of functions. Like the H is we sometimes call a formulaic function or an algorithmic function, and G is a lookup function or a discrete function. But what we're going to do is we're going to take some letter, like you could take the first one, A here, and then you could take some other letter, maybe the last one if you want, or the second one, whatever you want. But then go through this lookup table. Right, so you could take A, you could take if you wanted, you could take the first letter and the second letter, for example, if you want. So you could take A and U, and so you would use 0 and 21 and mod by some array size. And maybe that'll work, but chances are it won't, and chances are some of these guys are going to collide. So the way to fix that is you change the values in this G. Okay, that's what we did in the previous assignment, right? So that you need to hard code it and then manually adjust it. So what I would do is I would write a program that generates key values with some initial hash function. Generate all the keys and then look at them and see how many collisions you have. And then get into this G table and start changing values here and then rerun it and see if you have less collisions. And keep doing that until you have 0 collisions, right? You have a perfect hash. That's the definition of a perfect hash, is 0 collisions. Okay? So you might want to look at this Jabberwocky again, which I discussed in the last assignment, and there's a video explaining how this thing works. But the basic idea is I started with values 97 through 122. Here I'm using 0 through 25. It doesn't matter as long as their initial values are different. Like here, 97 through 122 is the ASCII value, because the code, I think, was a little easier to write in the language that I used. But as long as these are different values initially. Anyway, then fiddle with these values such that the result is that all of these keys are unique. And stored in the data array, that's what they look like. Okay, so you might need to review how this works and then get this in plain vanilla, simple C code. Get this to work. So this will be a expression in C, and this will be literally a hard-coded array in C. And then you need to figure out how to get the letters out of these strings and get them into this hash function. Okay, that is the assignment. I don't think there's anything else to say about this. There's part 1. You have to deal with the collisions. Part 2, you're going to spend all this time up front getting this to be a perfect hash, and you're just going to pump them into these guys, into this, pump the data into this array here. That's it. Have fun.